Okay, so I hope all of you are able to share, see my screen of the lecture notes. I hope.
Yes.
Oh, okay. So let us start then. Uh, very good. Okay. So basically, this is the second lecture of this course, Quantum Mechanics 1. So in the last lecture, we discussed black body radiation and Planck's quantum hypothesis on black body radiation. And in this lecture, we'll continue the discussion how the particle nature of radiation came into picture and how did all these ideas were experimentally verified. And we will, but before going into that, just for our like revision and beat recap, we'll just do a summary of our last class. So in the last class, what did we do? Basically we introduced what is a black body, right? So what is a black body and what is a black body radiation, and after that we described how the classical theory of black body radiation could not actually match the theory with the experimental results for high frequency regime. Uh, and then we introduced the idea of Planck, who first for the first time gave the quantum hypothesis in 1900 on the black body radiation. So, what was Planck's hypothesis, or to match the experimental data of black body radiation with his quantum theory, was that any uh, atoms of black body radiator surface, like atoms which are like harmonic oscillator, which shows motion like harmonic oscillators, have energy levels which are quantized. Quantized means they have certain energy levels. They cannot have all energy levels in a continuum way, but they have these certain energy levels equal to nh nu. Uh, sorry, equal to nh nu. So this was the quantized energy level introduced by Planck, where n is the number of integers 1, 2, etc., and h is the Planck's constant. Somebody join. Let me add. Okay, so this was the main idea of Planck black body radiation, that the radiation coming out from a black body surface has energies which are like quantized energies. Like it is always an integer multiple of some constant term which is h nu. Like it comes like h nu, then 2h nu, 3h nu, etc. So this was the idea that Planck introduced to actually match the idea of experimental data of black body radiation with his theory, and it was for the first time that the quantum idea was introduced to the uh, to the classical mindset of the physics world back then in the beginning of 20th century. Okay, so this was the summary of the last class, and we'll proceed from here on that based on Planck's idea. Later on, what Einstein did is that Einstein generalized this idea even a bit more. How is that he said that not only the oscillator atoms of the blackbody radiator, but any mechanical oscillator that has this simple harmonic oscillator kind of motion, these atoms will have energy levels which are quantized levels like this. Okay. So Planck said that it was specified for only blackbody radiators which have charged atoms that oscillate simple harmonically during radiation. But Einstein proposed that not only charged oscillators but any mechanical oscillator itself can have such quantized energy levels as demonstrated by Planck in this equation. Now he further added, which was his excellence, that he further added to this theory that not only the energy levels are quantized, but the radiation we are talking about, the blackbody radiation, suppose for this case, it actually behaves like a particle. Like radiation, we are accustomed that radiation will kind of behave like a wave, or it will propagate like a wave. But Einstein first time said that no, it is not just a wave, but it behaves like a particle when it interacts with matter. So no, somebody else has joined. Okay. So that is the thing that Einstein said, that when the radiation interacts with matter, it actually behaves like particles. Why particles? Because you see, the energy of the uh, radiation is actually quantized in terms of h nu. It's some bundle of energy h nu, like it's an energy bundle. Say it's an energy bundle concentrated, which has a certain amount of energy h nu, and the total radiation is consisting of many such h nu bundles. Let's say many such bundles are present, and the total radiation is composed of all these, and that's why depending on the number of n, we can decide how many bundles will be there, and therefore from that n can be 1, 2, 3, etc., any integer value. So from there, Einstein first had the idea that light or radiation can also be thought of like a quantized object, and this quanta, or this smallest form of energy bundle that the light can have, is termed as photon, which is a particle aspect of radiation that we'll come to know gradually in more detail during this lecture. But for now, let us just know this bit, that light has this particle-like nature, and this particle is actually termed as photon, and each photon has energy quantized as h nu. Okay, where nu is the frequency of the oscillation of the atom. Now, based on now Einstein gave the theory, and the experimental justification he actually explained to support his theory was this experiment called photoelectric effect. So that's why we will be discussing photoelectric effect in this class, because it will be very crucial for understanding the quantum phenomena and how this quantum phenomena came into account for all our subsequent lectures. Okay, so let us discuss then photoelectric effect. So you see, as the name suggests, the photoelectric effect has two parts. One is photo and other is electric. So photo basically means light. Okay, photo means light, and electric means it has something to do with electrons. So the name itself suggests the meaning very clearly, that photoelectric effect is something that because of the incidence of light, some electrons will come out from a metallic surface. Now, this is a simplified thing, okay? But if we discuss it in a bit detail, then we have to look at this schematic given here. Like in this schematic, we can see we have a metallic surface over here, which has lots of free electrons. These are all free electrons inside the metal, because we know metals are a carrier of free electrons or conduction electrons in a large amount. And electromagnetic radiation, this is the electromagnetic radiation that is incident on the metallic plate or the surface, and because of which some electrons come out from the surface, which we call as photoelectrons, because they come out absorbing the energy of light or photon. That's why we call it photoelectron. Now, why the electrons come out? The basic general concept we can have is that when the electrons are always bound by some kind of energy inside the metal, like it is bound to the atoms in the metal by some energy that is called generally the binding energy. Now, when the electromagnetic radiation is incident, now the electrons will absorb that energy from the EM radiation. Electron will absorb the energy. Now, absorbing the energy will make the electrons energetic enough, and they will be able to overcome this binding energy factor, and they will be able to come out from the surface thereby, and they will be emitted as photoelectrons. Now, this is the whole concept of photoelectric effect, that a light or radiation is incident on a metallic surface, and if the incident radiation is sufficient enough energetic, like this point, okay, another person joined. Okay. Okay, so in photoelectric effect, so we are discussing that the light or radiation is incident on the metallic surface, and as a result of that, the electrons that are present inside the metal will get energetic, absorbing that energy, and as a result, they will come out as photoelectrons. So this is the whole idea or simplest idea of photoelectric effect. Now, one thing that will be crucial in this case is the point that I have highlighted in here, that the light wave or EM radiation will have to have a sufficient energy to actually cause photoelectric effect. Now, what do we mean by sufficient energy? Like say for this what amount of energy will be sufficient for emitting electrons from a particular metallic surface will basically depend on the type of metal we'll be using for that experiment, because different metals have different characteristics. So different metals, the atoms and the electrons will have different binding energy of their own. So based on that, the energy that is required, minimum energy that is required for actually causing this photoelectron to come out, overcoming their binding energy from the surface will be different for different metals. Now, like say, mostly in photoelectric effect, we'll discuss about UV light or ultraviolet light, which has a shorter wavelength. UV light has a shorter wavelength. Sorry, wavelength lambda is shorter than visible light wavelength. Visible light means the light we see every day, like the light we see, the colors we see in everyday objects. So visible light wavelength lambda is basically greater than the UV light wavelength. So as a result of that, you see that lambda and mu, that is the frequency and the wavelength, are inversely proportional to each other. And because of that, UV light has a larger frequency than the visible light, which makes UV light much more energetic than visible light. And as a result of that, mostly metallic surfaces that shows photoelectric effect uses UV light to actually be on the safe side, that it will be enough energetic to actually emit any photoelectron from the surface. Okay, so that energy part is important, and as I said, that what energy will be sufficient for a particular metallic surface will be properly dependent on the characteristics of the metal only. Now, there is another important aspect here, that is called the work function W naught of a metal. Now, this is also a characteristic property of the metal. The definition of work function that I will discuss here is that basically work function is the so that is the pen go. So the yeah, so work function of a metal is basically the pen is having some problem. Yeah, it is the minimum energy. Work function is the minimum energy that is required for an electron to come out of a metallic surface. Okay, people are joining in between the class. So we learned that work function is basically the minimum energy that is required for an electron to come out of a metallic surface. Okay. So now this terminology will be important as we proceed through the description of photoelectric effect a bit more. But this is the generic idea that I explained to you, that light is incident or the radiation incident on a metallic surface, and as a result of that, the electrons from the surface will free get free from this binding energy, and it will come out as photoelectron. This is the idea of photoelectric effect. And the simplest example that we can see in everyday life, or as at least an application of photoelectric effect, will be the solar cells. So you see the solar cell, what they do, in solar cells they have this metallic plates on which the solar energy or the light from radiation from sun actually falls upon, and it what it does is that it stores that solar energy. Solar energy it absorbs, gets energetic, and produces photoelectrons. And we know photoelectrons producing means electrons means actually a mean of current. So current production. So so that's why it actually, what it does is that it absorbs the solar energy, and it converts that energy into electric energy. Okay, so this is the simplest idea. We are already all familiar with solar panel, solar cells, that it actually takes the solar energy and it converts that into electric energy, and that is used in most many of the electric appliances of our everyday use. So this is basically a simplest application that photoelectric effect can have in our daily lives. Now we describe the experiment that was first conducted on this photoelectric effect from the earlier times. So this is a brief historical background from describing from where it all started. So basically, this man is Heinrich Hertz. He actually, for the first time in 1887, did the experiment, which actually with two electrodes, he did an experiment to prove that electromagnetic radiation actually exists. And based on his experimental results, later Maxwell, he is another scientist, he developed the classical theory of electromagnetic radiation. Now, But the irony is that Harj, who himself basically by his experiments proved the existence of EM radiation, and based on whose experiments the classical theory of EM radiation was developed altogether. But ironical fact is that some of the experimental observations that he noted were actually later they played a very crucial role to actually introduce the or support the idea of photoelectric effect, which actually was the quantum theory given by Einstein later on. So we'll move forward to that in a bit. But for the moment, just let us know that Hertz in this experiment observed that the electric discharge between two electrodes, this occurred more readily when one of the electrodes is actually illuminated by some UV light. Okay, this was just a mere observation, and he did nothing about it, and he just let his conclusion done with the classical theory only. But then later on, another scientist, this Leonard, this man, he also did the similar experiment with some of his modifications, and he observed the same thing, and he explained that maybe the UV light is actually helping the discharge between the two electrodes because it is causing somehow the electrons to emit from the cathode surface. Now, this was the first like base point that was created for the photoelectric effect. You see, because this is the photoelectric effect, right? That light is UV light, be it any light, that UV light is incident on the metallic surface or the electrode say, and it is causing the electrons to come out from that cathode surface. So this is the photoelectric effect that was first discovered or invented, I'd say, uh, by this scientist Leonard in 1902. Now, now you see that this experiment and these observations are all okay, all right, but some some understanding or some observation of these experiments actually contradicted our generic classical wave theory of light. Now that's when the scientists had to choose that or scientists had to think about some other theory to actually resolve all these contradictions and to come up with some other theory, which was basically done by Einstein later on by his quantum theory of light, that he introduced that light is not just a wave but it has a quantum nature, and each particular energy bundle of this light radiation will be called as photon, which is a particle aspect of light. Now, before going on to what Einstein actually did, this is the experimental setup that I want to demonstrate to all of you for a better understanding of the experiment. So this is the experimental setup. This was the main experimental setup of Leonard that Leonard used for photoelectric effect in his lab. But this looks a bit complicated on the first look. So we'll just look at the simplest schematic, which is also equivalent to this diagram. We'll look at the schematic of this experimental setup for better understanding. So you see, we have a glass chamber which is completely evacuated. Like here, this chamber and this chamber is the same. So this is a evacuated chamber. Inside there is a vacuum environment, and this is two electrodes. One is cathode minus, and other is anode, denoted by C by plus. And from some quartz window that is placed somewhere above here, there is some quartz window from which ultraviolet rays are actually incident inside on the cathode plate, okay, cathode electrode. Like the quartz window is here in this case. You can see from this diagram, the quartz window is here in the schematic. So the incident light is coming on, and this is actually incident on the cathode plate first. So as a result, because of photoelectric effect happens, so it will cause the photoelectrons to come out from the metallic plate, and it will go this way. The photoelectrons are coming out. This is the pink dots you see. These are basically representative of the photoelectrons that are coming out from the cathode surface. And all of the electrons come out with different kinetic energy. I must mention that because different electrons will have different binding energies, different type of collisions they will suffer. So they will come out with different kinetic energies from the metallic surface. And now this we see, this is a voltage source or the potential that is connected between the two electrodes, which actually is giving a electric field or a potential drive to this whole system. And this G is a galvanometer that is actually connected to measure current in the circuit. This is to measure current in the circuit. Now this is the basic picture. Okay, now we'll see what is this whole setup doing, like what is the experiment that is conducted out of it. So basically, as I was mentioning that ultraviolet rays are falling on the cathode surface, and this is causing the electrons to come out from the surface as photoelectrons, and eventually the photoelectrons will also get a drive of the electric field that is connected over here, because you see that positive electrode is actually this electron and the negative electrode is this one, from where the electrons are coming out. So naturally the electrons, being a negatively charged particle, will be attracted towards the positively charged electron, and it will be readily moving towards this one. And in this way a circuit will be completed where electron is moving from negative to positive electron, and as a result sorry we will see a current flow in the whole circuit. Like electrons moving from this way to this way, that means we will see a current flow from this positive to negative, that means this way to this way. Okay, so this current will be measured by this galvanometer in over here, and this will be called a photocurrent because it is caused by the photoelectron. Now, what will be the current versus voltage curve look like from this experiment? So, this is the representative IV curve from the experiment, where the x-axis is for the potential or the voltage, and the y-axis is showing the photocurrent I. Now, let us first focus on a single curve. Like for a single, say we are focusing on this I3. Now, so for a single current versus voltage curve, we see that when the voltage or the potential difference is 0 between the two electrodes, even then there is a significant and finite non-zero value of current in the circuit existing. Like current is not 0 when voltage is 0. This is a very crucial point. And as the voltage is increasing, naturally the current will also increase at first, and then it will not increase anymore, rather it will get saturated at a certain fixed value. So if we just draw a straight line over here, so this is the saturation line where the current gets saturated and fixed. This is the I3 line here, and current cannot increase anymore from here. And from the zero value, if we decrease the voltage towards a negative value, that is if we apply a negative potential between the electrodes, then we will see that current will gradually decrease, and at a certain value, that is the Vs, or the negative stop potential, that is called stopping potential Vs, is the potential value where the circuit current will be completely zero, because here you see that I equal to 0 at this point. Now this is the phenomena that is going on here. Now what is the physics behind that is causing all such things? So if we try to explain it simply, then basically what happens is that the electrons that are coming out from this cathode surface will have initial sufficient kinetic energy of their own. Now some of the electrons will have enough kinetic energy such that even if we don't apply a voltage over here, that is even if the voltage is 0 over here, then also the electrons will have enough kinetic energy to actually move from here to here by its own kinetic energy, and thereby there will be a continuous flow of electrons giving a certain non-zero current I not equal to 0 at even V equal to 0. That's why in this curve we are seeing an offset current even at V equal to 0. Alright. And now, as we increase the voltage, like say as we are giving some finite voltage over here, that is this electrode becoming positive little bit, and this is remaining negative. So then naturally the electrons that were already anyway moving will now actually uh, experience some attractive force from this positive electrode, which is like a potential drive, and because of that the electrons will be more readily moving towards the opposite electron. Now, as a result of that, some of the electrons that might have smaller kinetic energy and were not able to reach towards this anode earlier times when the potential was 0, will be able to reach the other side, because there is some non-zero potential drive that is applied to the electrons here. So, because of that, the current actually increases when voltage increases. Okay, but the interesting fact is that the current does not increase limitlessly as we keep on increasing the voltage. So even if we keep on increasing the voltage, there is some point when the current gets saturated to some value. Let's say this is the saturation current we denote by IS. So this is the value of the constant saturation current value. It comes when all the electrons that are photoelectrons emitted from this cathode are actually finished. Like all the electrons that are produced are actually moved to the other side. There are no photoelectrons left to be emitted and to go to the other side. So since no photoelectron is left anymore, so we will not be able to produce any more current, and eventually the current will be fixed to a certain saturation value that is denoted by in this graph, that is in this case I3. So here for this curve, I3 is this IS value, that is the saturation current value. Okay. And for the last part, why this current is decreasing when we are applying a negative potential is because, uh, let's say in this diagram, if you are applying a negative potential, uh, what will that mean? That will mean that we will be reversing the polarity of this voltage source. Like previously this was at negative and this was as positive, but when we'll be applying a negative voltage, then we'll basically be reversing the polarity from this end to this end. Like this part will be negative here and this part will be positive. So basically that means this electrode over here will now be as a positively charged electrode, and this will be a this will be a negatively charged electron, and this will be a positively charged electron. Now we know that electrons are negatively charged particles, so they will basically be repelled from a negatively charged electron. So this will actually oppose the electron's motion towards this opposite electron, and that's why, because this is already like working like a opposing motion to the electrons, generic kinetic energy and generic motion. Because of that, so because of that opposing motion of the reverse field, opposing field we will be applying for the negative direction. Because of that, the current will gradually start to decrease as we increase the voltage in the negative side, as we increase the voltage in the negative side. Okay. And at some value, which is this stopping potential value Vs, so at V equal to Vs, which is obviously in the negative side because it is reversed in polarity, at some value the current in the circuit becomes zero, because obviously you see that the electrons are coming with some kinetic energy of their own. Okay, electrons are trying to move forward in this case towards this electrode, but then this electrode is already being a negative electrode. So now this will try to repel the electron coming from towards it, and because of that it will give a opposite force to the electron. And when these two energies, like the kinetic energy of the electron and the maximum kinetic energy of the electron can have, and the maximum potential that the that can produce this opposing force to stop even the maximum kinetic energy electron, will actually be equal, then that is when Ke max equal to, say if this potential is Vs, then we know that potential times charge actually gives us the energy, dimension of energy. So basically when Ke max equal to EVs, then we will see that the current in the circuit becomes zero, because simply no electron is enough energetic, or no electron is fast enough so that it can oppose this opposing force of the electric field, or say the potential over here, and it will just suppress all the current or all the electron motion in the circuit. And because of that we call it stopping potential, because it is a generic name that it is stopping the current flow in the circuit, so that's why it will be called a stopping potential, or Vs. Now now, now let us look at, so this is the basic, like the observation that the experimentalists actually observed from the photoelectric effect setup. But now there are some key observations that will be crucial for the quantum aspect, for introducing the quantum aspect. So those observations are: number one, that if we increase the intensity of the incident radiation, that the light that is incident on the metallic surface, if we increase its intensity, then it does not change the value of the stopping potential Vs. Or Vs, we see that it is closely related to the kinetic energy, maximum kinetic energy, or K max of the electrons. So basically we can say that Vs is actually kind of related to the kinetic energy of the electrons, and that's why intensity of the increasing intensity of the incident radiation. So increasing the intensity of the incident radiation will only increase the saturation current value, and it will not be changing anything in the stopping potential or the kinetic energy part, because this is evident from this curve only, that in this curve we are seeing this I versus V diagram for three different intensities. Like this is the intensity you are seeing by this arrow, this is indicating that towards the from bottom to top the intensity of the light is actually increasing, and because of which what change do we see in the curves? We see that the curves actually all are meeting at the same stopping potential Vs, that is not changing. Only the saturation current value is changing for different cases. Like the saturation current value for the maximum intensity here has a maximum saturation current Is equal to I1, and the case where the intensity is the lowermost, there will have the saturation current value I3 to be lowest of all. So basically this is a proportionality relation that as intensity of the incident radiation increases, then the saturation current value of the circuit also increases. That's why in this case I3, I1 is greater than I2 greater than I3. So this is all the saturation current values described over here. This is this is actually proportional to the intensity of the incident radiation. But surprisingly, the Vs in all cases is same. That Vs is not affected by the change of intensity of the incident radiation. So this is one observation. And so the second observation is from this curve. This is also a current versus voltage curve where we keep the intensity of the radiation fixed. Like previous case, we vary the intensity of the incident radiation, but in this case, we keep the intensity of the radiation fixed. And instead, what we'll do is that we change the frequency of the incident radiation. Frequency means mu of the incident radiation. Okay. So like in this case, you can see that we have used three different frequencies, mu1, mu2 and mu, which have a relation like mu3 is the greatest of all, then mu2 and then mu1. Okay. And what change do you see in the curve because of this change? We see that the saturation current value, which is Is over here, is fixed for all the cases. Like changing the frequency does not change the saturation current value. What it does instead is that it changes the stopping potential value, which was constant in the previous case, if you remember. That these two cases are exactly conjugate of each other. Like when we are changing the intensity or increasing the intensity, we see only the saturation current value is increasing, right? But the stopping potential or the kinetic energy of electrons remains the same. But when we are keeping the intensity fixed and we are changing the frequency of the radiation, then the saturation current value remains fixed and the stopping potential value changes. So in this case, Is is fixed in all cases and the stopping potential Vs, or here in this image they have denoted Vs as V naught. This is changing because of the frequency change. Now that how is this it changing? It is changing linearly to the frequency, because if mu3 is the maximum of all, then we see that for mu3 the stopping potential in the negative side has the maximum magnitude, maximum absolute value. Because it is a negative potential, so we will consider the absolute value of that. So we see for mu3 the maximum, the stopping potential has the maximum absolute value, and then for mu2 it is in the middle range, and for mu1 it is the lowest. So basically, the stopping potential here is actually uh, changing. Of course, the absolute value don't mix up with the sign and all, which is absolute value of the potential is actually changing as mu3 or the frequency is varied for the different radiation. So this is another observation. And the final observation that will be very crucial is that there is always some cutoff or threshold frequency that is existing in the circuit, which is denoted by nu naught. Now, this is called a cutoff frequency because below this frequency, if the incident radiation has a frequency that is less than nu naught, that is the cutoff frequency, then we will see no uh, no photoelectric effect to be happening in the circuit. So this is a curve of stopping potential Vs versus the frequency of incident radiation. Say we denote it as mu. Then we see that these red curves are actually the graph showing the relation between both of them. So it shows that two different metals have, of course, two different cutoff frequencies, as I have mentioned over here also, that this mu naught value depends on the characteristic of the metal surface. Like what metal we are using, that decides what cutoff frequency value we will be having. So for example, we have metal A, then it will have a cutoff frequency nu naught A, and for metal B, we will have a cutoff frequency nu naught B. Okay, and so you see that for mu less than mu naught, for any case, say for A case, if mu less than mu naught A in this region, there is no curve, right? So there is, because the effect is not defined over here, because the photoelectric effect cannot even occur when the frequency of incident radiation is less than the cutoff frequency. And similarly for B also, metal B also, if in this whole region for B, where mu is less than mu naught B, then no curve is seen, because in this region the metal cannot have photoelectric effect happening. Only when this frequency exceeds the cutoff frequency value, that is for nu naught A, and that is here for metal B, this is nu naught B, then only we are seeing such curves. So this is an interesting observation that photoelectric effect has such cutoff frequencies nu naught that at nu equal to nu naught is the threshold. Nu greater than nu naught, this value will decide that the photoelectric effect will start. Photoelectric effect occurs for this value, and for nu less than nu naught, nothing is seen. Alright. So this is precisely the case, and also mind that whether the photoelectric effect will happen or not will not, like if the frequency is nu less than nu naught, then even if the incident light radiation is very intense, how even if how much intense it is, it does not matter. Like even that intense radiation cannot also cause the photoelectric effect to happen. So this solely depends on the frequency that actually decides that whether the light source is feeble or intense, or whether the irradiation time, that is how much time we are giving for the metallic surface to actually be illuminated from the radiation source. All of these things becomes irrelevant to show a photoelectric effect once the frequency of incident radiation is smaller than nu naught. So this is very crucial that we should always be at a frequency that is greater than this cutoff value to actually see the photoelectric effect. Now we'll see the details idea of that later in the experiment of Millikan also, who proved this experimentally, this card. And so for now we move on to the like description of the effect, the key observation that we have noted from here. Okay, so three observations we have noted is that one is that changing the intensity of the radiation does not change the stopping potential or kinetic energy, it only changes the saturation current value. And second is that changing the frequency of the incident radiation, keeping the intensity fixed, does not change the saturation current value, it only changes the stopping potential values. And that also is linearly proportional to the frequency change. That means if the frequency is increasing, then the absolute value of the stopping potential will also be increasing. And that will subsequently mean that the maximum kinetic energy of the photoelectron is also increasing, because we see we have also already mentioned that maximum kinetic energy of any photoelectron, that is half mv square max or k max, will be equal to minus E times Vs, where Vs is the stopping potential. So that's why k max is actually proportional to Vs. So Vs increasing means k max is also increasing. And third important observation is that there is always a cutoff frequency that depends solely on the characteristic of the metal we are using, and if we are below that frequency we will not see any photoelectric effect to happen even if we have an intense enough light source. But if we are greater than this new naught or cutoff frequency, then we can see the photoelectric effect to happen even if our light source is feeble or we have used a very small time to illuminate the surface. So this is the observations, and now we move on to why this experiment actually showed the failure of classical theory, like why it cannot be explained using the Maxwell's classical theory of electromagnetic radiation. Now the first point is that the first observation is we noted that the kinetic energy of the photoelectrons or the stopping potential in case is actually uh, does not depending on the what is the intensity of the incident radiation. But classical theory suggests that the intensity of the intense radiation must be controlling the kinetic energy of the photoelectrons. Why? Because say in classical theory light is considered as a wave, right? So it is like a wave, that is an electromagnetic wave which has a oscillating, because it is an electromagnetic wave, so it has a oscillating electric field component with the amplitude E vector, and its intensity will be proportional to the amplitude square, that means E square. The intensity of the radiation will be proportional to the electric field amplitude whole square. And because of this field it will apply some electric force on the photoelectrons, which is F equal to E times the electric field, and this force will actually cause the electrons to absorb energy from the wave or whatever, and that will give energy to the photoelectron. So basically if we see the stream of the processes, then we will see that when the amplitude of the electric field increasing, that means the intensity of the light will increase, and that will decide that the uh, energy that photoelectrons actually absorb from the light that is incident will also be increasing. So classical theory or the wave theory of light basically suggests, or if it is true, then it suggests that the kinetic energy of the electrons or the photoelectrons that are emitted should sorry should should depend on the intensity of incident radiation. Okay. Because here light is treated as a wave. Okay. Okay. So here light is treated as a wave. So that's why we are saying that this should be the case if classical theory were to be true. But here we already have seen from the observation that this is not true. This is basically the other way around, that the kinetic energy of the photoelectrons is independent of the intensity of the incident radiation. And now the second point is that the wave theory says that the photoelectric effect should occur at any frequency, provided that the light is intense enough, that light intensity is enough to like give the enough energy to the electrons, and the irradiation time, that means how much time we are giving for the light to illuminate the metallic surface. These two parameters will be should be enough for the photoelectrons to collect enough energy from the photons. Sorry, now the idea of photons have not yet been introduced. So the energy it is being absorbing from the incident light. So it should be enough for the ejection of the photoelectrons from the surface. So only these two parameters should be important. It does not matter what frequency of light we are choosing. Only the light should be intense and the radiation time should be enough for electrons to get enough energy. That means it should not depend on the frequency, and there should not be any cutoff frequency like we have observed in our experimental observations, that this there is a cutoff frequency nu equal to nu naught, and if the incident light or radiation frequency is less than that, then we will not have any photoelectric effect, no photoelectric effect from that, even if we are using a very high intense light source or we are giving a large enough time. So this is also a case where the experimental evidences are going against the classical theory prediction. Okay? And the final one is that the classical theory says that light energy is uniformly distributed over the wavefront of light. So when we are using a very feeble enough light source, suppose which has a feeble intensity, then it will be continuously supplying energy to a certain portion of the surface where the electron is sitting, and for the electron to collect enough energy from that wavefront or from the little part of the wavefront that it can access, so there should have some reasonable time gap between the incident of the radiation on a surface, incident of the radiation age, and the electrons coming out from the surface. So there should be a significant time gap, suppose in seconds or minutes, between that are actually measurable experimentally, like measurable in experimental time scales. So that is true when wave theory is correct. That if wave theory is true, then there should be a certain time lag between the incidence of radiation and the emission of photoelectrons from the surface. But in reality, in experiments, the people have observed that the process is totally instantaneous. Like the incident radiation is coming on the surface, it hits the surface, and as soon as it hits the surface, the photoelectrons come out very spontaneously and very instantaneously. Like there is no measurable time gap. Like even if there is a time gap, it is so small, even if nanosecond and smaller order, that it cannot be actually measured experimentally very clearly. So it is like an experiment. It is like an instantaneous process in reality, whereas classical wave theory suggests that it should be a there should be a time lag between these two processes. So now these three are the 3 points that are crucial from the observation of the photoelectric effect experiment, that actually oppose that the classical theory of EM radiation is not applicable for explaining this phenomenon. So now then in 1905, the genius Einstein, he came with a new theory of his own. So basically, he had initial idea from Planck's hypothesis that the quantum idea, that the something like a quantum should can exist in nature, and from that experience, he actually questioned the classical theory of EM radiation in the photoelectric effect case, and he explained his own quantum theory to explain this phenomena. And for a supporting evidence, he used photoelectric effect observations. So this was the support of his theory, because the theory he gave was very able or very justified to actually explain all the contradictions that were coming from the classical theory and the experimental results. Okay. So initially it was not very recognized, but later on when it was proved experimentally to be true, by some other experiments. Then Einstein received a Nobel Prize in 1921 for this discovery of it. Okay. So now we'll be interested to know that what exactly he proposed that caused all this difference. So basically, he proposed that the radiant energy that we had already known that it is quantized, like it has some proper allowable values like h nu, 2h nu, 3h nu, etc. He said that not only the energy levels are quantized, but the radiation itself is coming like a quantized packet, or it is coming like a bundle that I have previously mentioned. Like it is not a continuum energy, like it can take any energy value it is possible. It is the classical idea that energy continuum exists, that energy can take any value possible. But here the quantum idea says that no, energy cannot take any random value, but it has some allowed energy levels which have some certain defined values like 0h nu, 2h nu, etc. Now we see to go from one level to another level in this quantum case, like say we want to go from h nu to this ground state 0. Now for that what we have to do, we have to just emit some energy h nu and go to 0. Similarly, to go from h nu to 2h nu state, we have to absorb some energy, that is the excess energy, that is h nu in this case. Now, even if we want to go from 0 to 2h nu, then we have to absorb energy of 2h nu, right? So basically, all this case what we are trying to explain from here is that uh, basically energy has some certain quanta which has the smallest value given by h nu. Because you see, every time we are trying to go from one level to another, we have to either absorb or emit some amount of energy that is some integer multiple of this h nu energy value. So why not consider this h nu as a discrete energy packet? Like it is a packet of energy which has the energy fixed as h nu, like a discrete energy packet or bundle. And the whole radiation that we have previously considered as waves are actually like this collection of so many such bundles that have all each energy h nu. Now these bundles are actually called as photons later, which is the particle aspect of radiation. Like the radiation that was initially considered as wave like radiation, now in this new quantum theory idea is supposed to be particle like, or at least it behaves as a particle when it interacts with a matter, and this particle like form is called photon. So photon is basically, what is photon? If we say in one line, it is basically the quantized form of the energy. Okay. Now there are some important points that I have just noted down here, that so if people can ask then why radiation is behaving wave like when we apparently seeing it propagate. So Einstein had explained this fact as that when it is propagating, the waves are behaving almost like a, sorry, waves, not waves. The radiation is almost behaving like a wave, because then it is showing just an average behavior. Because there are so many large number of photons present over there that we cannot almost like distinguish between each separate photon's existence, and in an average behavior, it almost behaves like a wave. But when it interacts with a particle with matter or some particle, then it has some individual existence, and then the photon aspect or the particle aspect of radiation becomes more prominent. Okay. So now also another thing Einstein assumed for simplicity is that each photon in this photoelectric effect, that is each photon from the incident radiation, gets completely absorbed by each electron in the photocathode. Like one electron absorbs one complete photon in the photoelectric process. So if we go by that theory, then we say this say one photon that is incident has energy h nu, which is absorbed by the electron, one single photoelectron, and that electron has some work function W, that is the energy it has to overcome or it has to get to actually come out from the metallic surface. So this energy it has to be lost, because this amount of energy is lost from obtaining the electron to come out from the metal surface. So what is the excess energy or the rest energy? That goes like the kinetic energy of the coming outgoing electron. Like the electron is absorbing the photon's energy entirely, that is h nu. It is using some part of that energy to actually come out from the metal surface, come out from the metal surface. So that's why the work function comes, depends on the metal nature, and the rest of the energy is used up as the kinetic energy of the outgoing electron. This is the general form. Now, for the faster rejected electron that has the maximum kinetic energy over this bunch, we'll have the maximum kinetic energy K max. So obviously when K is maximum, then obviously this energy W will have to be minimum. So that is the definition of work function in particular way, that when W is minimum, then it is W naught. That is the real definition of work function. That is the minimum energy that has electron has to uh, use to come out of the metallic surface. So from that we see this equation is coming, that K max equal to H nu minus W naught. And also not to forget that K max is actually related to the stopping potential by E times Bs, where Bs is the stopping potential. Okay. So from this equation itself, we can see from Einstein's first idea that this K max, the kinetic energy maximum of the electrons, maximum kinetic energy of the electrons, in no way it depends on the incident intensity of the light, because you see in this equation, this work function or this energy, this H times nu, in nowhere we can see the intensity term of light, but it is actually proportional to the frequency of light, that is nu. So here we can resolve the first point. What is the first objection from the classical theory results and the experimental results, that uh, the kinetic energy of the electron should be proportional or should be dependent to the intensity of the light, but experiment showed that it is not true. So this was the reason that the kinetic energy is actually not dependent in any way on the intensity. It is rather dependent on the frequency. So then if we use more intense light, that means we are using intensity means number of photons it is carrying, the wave is carrying, the number of photons per unit time per unit area. So more intense light means more number of photons per unit time, and that will just mean more number of photoelectrons coming out per unit time, because we have already discussed this, that Einstein assumed that one photon is equivalent to coming out of one photoelectron. Okay. So naturally, if there are more number of photons per time, so there will be more number of ejected electrons per time. So that means there will be more photocurrent. So because of this result, because of this conclusion, we saw in this graph above here that uh, when we are increasing the intensity from bottom to top, then the kinetic energy that is related to the stopping potential did not change. Rather, the saturation current value also increased, is because the number of photoelectrons is getting increased, because number of photons increased from intensity increase, and thereby we are getting more current. So this is clear, I hope. And then we come to the second objection, that was the objection of classical theory into the experimental result, that there is why there is a cutoff frequency, like why there is a nu naught certain frequency below which the photoelectric effect cannot happen. So this also we can resolve from this equation itself. Like if we put on K max equal to 0 in this equation, that the coming out electron has no kinetic energy of itself, then H nu becomes equal to the work function W naught. Now this particular frequency where H nu becomes W naught, we denote this frequency as nu naught here. So when K max equal to 0, H nu naught equal to W naught. So this nu naught is actually the cutoff frequency value that we discussed in the experiment. Like you see that in general idea what we can understand is that the electron that is coming out from the metallic surface, okay, so it is able to come out from the metallic surface because it has enough work function energy to come out, all right. But if the electron just comes out and it does not have any kinetic energy to actually speed it up, then there is no point, like there will be no motion of the electron, and if there is no motion of the electron, that means there is no current. So basically this is the reason why if nu is less than nu naught, then one cannot have any current in the circuit, because of this condition, that at W naught equal to H nu naught only K max equal to 0. So only when this nu is greater than nu naught, that means this H nu part is greater than H nu naught, that means H nu part is greater than W naught, because here you see we denoted H nu naught equal to W naught. So this is when the K max equal to H nu minus W naught equal to positive. So that means then will the electrons have a positive kinetic energy to move around, and it will then cause the photocurrent to happen. So that is the reason why we are getting no photoelectric effect or no photocurrent for nu less than nu naught, and we are only getting photocurrent for nu greater than nu naught when the electrons have certain kinetic energy, non-zero and positive. Okay. And for the last objection, this was that the why there is not any time lag between the incidence of the photon or incident of the light and the emergence of the photoelectron from the surface. So why this process is instantaneous in reality? This can also be explained because, see, in classical theory, what caused the problem is that we considered light as waves. So generally waves means it is incident on the surface and it is, say, accessing some portion of the surface where the one photoelectron is sitting, and this is the light that is coming. So the light's energy is actually uniformly distributed throughout its wavefront. So it is not like concentrated on a single part, it is uniformly distributed. So the certain amount of area of the wavefront that this electron can access is actually very small, very small, right? So for the electron to get enough energetic to actually come out of the metallic surface by overcoming all the barriers will be quite high, like the energy will be quite high for that. So to collect that amount of energy from this incident light and the wavefront's uniformly distributed energy, it will take very large amount of time. Even if it takes more time, if the light source is itself very feeble, like its intensity is very small, then it will take a larger time to actually collect that amount of energy, and after it collects the energy, then only the electron is able to come out. So necessarily there is a time lag between the incidence of radiation and the electron to come out. But this is the classical idea, all right. The quantum idea has no problem like this, because the problem is solved here, because the incident radiation here is not like a wave, not like a wave. So it is like a particle. So it is like many bundle of such particles is coming, and this is just hitting the surface of the metal. Each of these quantized bundle of energy has concentrated energy termed as h nu, and which is like each photon's energy. So one of the photon is coming, it is hitting the surface, and it is getting one photoelectron over here, and this photoelectron emits the absorbs the entire photon that is heating this, absorbs the entire photon, that means after absorbs the entire h nu energy, and that's why it immediately gets as soon as it gets hit by the photon, so it immediately gets energetic, and it starts doing all the processes that are followed afterwards. That means it actually first comes out by using the energy W naught, then the rest of the energy it is using at the kinetic energy. So that's why you are seeing this process is instantaneous, because as soon as the particle form or quantized form of the concentrated energy from the light is hitting the surface, it is actually making the electrons energetic enough, and it is coming out right away. So that's why the quantum theory is able to explain the fact that this photoelectric effect is actually an instantaneous process. Alright, so all the observations that were actually raised from the classical theory are already resolved by the quantum theory given by the idea of photon by Einstein. Okay? So now these are the some important expressions that will be important for us that I have already derived, but this is just written for a more clarification that the stopping potential EVS equal to h nu minus W naught. This comes because the kinetic energy maximum is previously written as h nu minus W naught, and kinetic energy maximum is also written as EVS. So that makes both of them equal, and this is equal to h into nu minus nu naught, because we have already said that h nu naught equal to W naught, that is the work function. Now, this formula will be very important even in application of sums, etc., that we generally face in such related problems in quantum physics or quantum mechanics. I'll give you some of the example sums to have a flavor of that, but these are the formulas that will be essential. And another is this formula, which is again a derivation from this formula itself, because here you see, if we divide this EVS equal to h nu minus nu naught by E on both sides, then we'll have this h by E times nu minus h by E times nu naught. So basically this is the second expression. Here Vs has a linear relationship with nu, where it has a linear y equal to mx plus c type of equation, straight line equation basically. So this is the case. Now I have just mentioned the famous experiment by Millikan in 1914, which actually finally confirmed that Einstein theory of photoelectric effect was actually true and actually correct. And he also determined the value of Planck's constant H, which was almost in the accuracy of 0.5% of the real value that is accepted now. That is the real value of H accepted now is 6.16 10 to the power minus 34 joule into second. And the value that was calculated from the experimental results of Millikan was almost plus minus 0.5% accuracy from this value. And this revolutionary result actually got him actually helped him to get the Nobel Prize in 1923 also. So you see this single experiment actually uh, helped two people to get the Nobel Prize. One is Einstein for giving his phenomenal theory, and one is this Millikan who actually proved this theory correct by his following experiment. Okay. So this is the simple setup of Millikan. I will not go into very detail, but this is for your understanding and knowledge that this is just a vacuum chamber again, where this is a rotating this kind of thing that can be rotated from outside manually, and this has three different kind of metals on three different parts. So whichever metal we want to use, like this is a potassium, this is lithium, this is sodium, whichever metal we want to use, we just we just rotate it, and we just metal that face the light path is actually the experiment uh, is carried on that metal. And this is the light window from where the monochromatic light of a single wavelength comes and falls onto the metallic surface. And this is the voltage potential applied from between the uh, like electrodes, like we have given in the earlier picture. And there is also current meter. This is microampere measuring current in the circuit. So basically, Millikan did the same trust thing in a bit different way, that he actually for a certain metal, like say when he's using sodium, then he's illuminating it with a monochromatic light, and he basically is changing the wavelength of the light to different values, and for different wavelength value, he's measuring what is the voltage or what is the potential at which the current in the circuit becoming zero. That means he is measuring the stopping potential Vs for each value of the wavelength of light, and from there he has obtained this curve stopping potential Vs versus different frequency means wavelength, because they are actually inversely proportional and related to each other, different frequency of incident light. And he found that they have a relation like this, like they have a linear relationship. This kind of relation you see we have seen from Einstein's theory right above here, that Vs equal to h by E into nu. So this is the y equal to mx plus c kind of straight line equation, because if we see y equal to mx plus c, then y versus x becomes a straight line with m equal to the slope and c equal to the intercept. That means the point where it cuts the y-axis. So in this case, the slope is basically following the Einstein equation, that this is equal to h by e times nu. So this is the slope m. So this, if we draw a tangent over here, this will give us a slope from this straight line. This will actually this helped basically Millikan calculated the slope of this line, and from there he actually got the value of the Planck's constant h. And also there is another term, that is minus h by e times nu naught, which is actually minus w naught times e, because h nu naught equal to w naught, the work function. So if we just extend this line, if we say this is not possible in reality, but for calculation sake, if we just extend this line hypothetically, then at some point it will cut the y-axis. That will be the intercept point of y-axis. Like that will be the value of minus w naught by a. So if we extend this just hypothetically, then we will also be able to calculate the w naught, that is the work function of the metal that Millikan used. Okay. And for more accuracy or more confirmation, he have put the option of all these three different metals, not only just a single metal. He have chose to do the experiment for all three different metals, and he has obtained the same result for all the cases. So that's where the Millikan's experiment in 1914 actually proved the Einstein theory predicted long ago in 1905 to be exactly true, because you see this match this equation. This also again shows the existence of such a cutoff frequency nu naught, because less than nu naught there is no stopping potential value, no photoelectric effect existing, and only for nu greater than nu naught it starts. So again this is a proof, experimental proof. This is basically the same thing, but here they have shown for two different metals. So basically for two different metals the work function will be changing, because this is a characteristic of the metal, and as a result this nu naught 1 and nu naught 2, that means the we have already said that this cutoff frequency also depend on the type of metal. This will also be changing, but the slope is remains the same. That's why they are two parallel lines, because they have same slope h by e, because h by e is a universal constant, e is a universal constant, h is also universal constant, so the slope of the line will be constant. Only the intercept value will be different for depending on the different work function of the metals, and the cutoff frequency values will be different depending on the metal. This is the basic equation that is followed here. This is the linear dependence, and as I said, he was able to determine H within such greater accuracy. Now this is what concludes the photoelectric effect. Now we'll just briefly discuss the Compton effect, and we'll see how this also supports the, I mean the what I say, that the particle nature of the radiation. Okay. So this was another form confirmation of the particle nature of radiation given by Compton in the year 1923. Okay. So what he did is that he chose a monochromatic X-ray source, and the X-ray beam he used was hit onto a graphite substrate, graphite surface. He was just, or was it like a target on which the X-ray source and the X-ray beams are hitting on, and from there the photon gets scattered, the light ray gets scattered, and there is a detector here which actually detected the scattered intensity versus wavelength of the radiation that is scattered. And from the experiment, this was the curves that are obtained for different scattering angles theta. So basically, I'll explain that in a bit detail gradually. But for a one-liner, let us just say that he actually used monochromatic X-ray beam and scattered that from a graphite surface, and he observed that the scattered wavelength of radiation lambda prime was different from the incident radiation, that was lambda, and not just different, all the time this lambda prime was greater than lambda. That means the scattered radiation becomes larger than the incident radiation. Now this excess wavelength, that is lambda prime minus lambda, this is called as delta lambda, which will derive generically that it will have an expression like this: h by mec 1 minus cos theta. Theta is the scattering angle of the radiation, scattering angle, like the angle at which it scatters because of the collision with the graphite target. And this h is the Planck's constant, c is the velocity of light, this is a universal constant, and me is the rest mass of the electron on graphite substrate on surface. So why we are calling it rest mass? Because there is another concept in physics. I don't know whether all of you are familiar or not, but I'll just discuss in a line that rest mass is basically a mass of a particle when its velocity equal to 0. That is, it is in rest. So then its mass will be called its rest mass. Let's say we are generally we are denoting this rest mass as m naught. But when the particle's velocity is not 0, that is, it is not in rest, then it will have a different mass that will not be same as the rest mass. In that case, this m naught will be m naught divided by 1 minus root over of v square by c square, where v is the velocity of the particle and c is the velocity of the light. So this is called relativistic mass, that happens when the particle's velocity is non-zero. Normally, in most of the cases, we generally, since the velocity v of the particle is much smaller than c, that is v by c is much smaller than 1, then we see this denominator part, this v by c much smaller than 1, then it can be taken as 0 with respect to 1, then m is nearly equal to m naught. That means if we are considering a particle that has a velocity non-zero but much smaller than light, that is happening in our everyday case, like most of the cases, like no matter how fast the train is moving or how fast the aeroplane is moving, its velocity is far smaller than the velocity of light, that is the highest, that is 10 to the power 8 meter per second. So in that case, all of these things are actually moving non-relativistically. We'll say the term is non-relativistic because it is moving at a velocity much smaller than the light's velocity. So in that case, we can approximately say that its mass is equal to, nearly equal to, the rest mass. But if we say the energy of the particle is moving, velocity of the particle is almost comparable to the velocity of light, or even if it is greater than the velocity of light, which is very rare and this is almost an impossible case. But in those cases, we cannot just ignore this term like we did here, like we turned it to 0. We cannot just ignore it like that. And in that case, the rest mass is not equal to the total mass of the particle. So that's what the idea of the rest mass and relativistic mass comes. But in this case, me that we are denoting in this expression is actually the rest mass of the electron, because the electrons that are present in the graphite are considered to be free electrons and stationary electrons. That means they have no velocity, they are fixed in space. And this H by MEC, this term is called lambda c. This is the Compton wavelength. This is the standard value, because you see this H, C and ME, all of this has a constant universal value. So this value of lambda c is also universal constant. Now, also we'll demonstrate that for classical theory to be true, if the classical theory was true, then even in Compton effect experiment case, the intensity of the scattered wavelength of the scattered radiation should not be different from wavelength of the incident radiation. So both of them should be equal. That means delta lambda should be 0 if classical theory was true, classical. But surprisingly enough, or not so surprisingly enough, because we have already seen that photoelectric effect suppose that radiation is not classical wave, rather it is quantum and it is like a particle nature. So that's what concludes in this experiment also, that delta lambda is not 0. So that's why it is not following the classical nature. It will have some other theory to explain such phenomena. That will obviously be quantum, that we'll see in a bit. So this is the basic experimental setup, that we have an X-ray source. Basically Compton had an X-ray source, and this is the collimated slits, that actually collimated means focus the X-ray beam even more. So this X-ray beam has a particular wavelength lambda, with which it is hitting the graphite target surface over here. And from the surface it is actually, because it is heated, so it is actually scattered off from its actual path. This is the dotted line that would be its actual path if it was not scattered. Then this is for scattered path, and the angle between both of them is theta, that is the scattering angle of the incident radiation, or scattered radiation. This is the scattering angle. And the scattered wavelength is different from the incident wavelength because it is termed as lambda prime. And this is just a detector which actually can move from here to here all through this dotted line. And thus for different value of theta, like if detector is placed here, then we can say that the theta is this part. Okay. So thus for different value of theta, we can place detector at different positions, and this detector can actually have the capability to actually observe the intensity of the scattered radiation versus their wavelength. This is the respective plots that are found generally by the experiments on the right hand side. Only the difference is that these are for different values of theta. Like for theta equal to 0, we see this is the intensity versus lambda plot. This is for theta equal to 90 degree. This is for theta equal to 45 degree, and this is for theta equal to 135 degree. Now, one thing is actually similar in all of this is that you see that when theta is equal to 0, there is only a single peak. Alright, and that is a lambda naught. Here in this case, lambda naught is the incident radiation wavelength. Incident wavelength of radiation. Now when theta is equal to 0, that means scattering angle is 0, then we will not see any other peaks, we will have a single peak. That means the scattered intensity, the scattered light have the same wavelength as the incident light, and which is equal to lambda naught. That's why you are getting only a peak at lambda naught. But when we are moving to a non-zero scattering angle value, that means it is actually scattered by some non-zero angle, like for theta equal to 45 degree, we see that gradually there is a second peak appearing, this one, other than the lambda naught. So there is a different wavelength that is present, that is lambda prime other than lambda naught. So that's why whenever this is scattered at some angle non-zero, this will have a different wavelength present, that is denoted by lambda prime, and which will be different from lambda naught, not equal. And this is the main observation from the Compton effect experiment, and we'll explain how this actually contradicts the classical theory. And naturally, if we increase the angle even more, like say from 45 degrees, we fix it at 90 degree, like the detector is like this. This is the graphite crystal. This is the incident light on it. This is the apparent direction of light if it was not scattered. And this is the 90 degree, just be a little bit, like I have drawn the line a bit curvy. It will just be a straight line and this out of plane, like this is a 90-degree angle. So if the light is scattered by this is lambda prime, this is lambda, then the detector is put like this to actually see the intensity of the scattered light at 90-degree angle. So for this case, we see that the peaks are even prominent. Like initially, the peaks were very close by and will not be able to very prominently separate it. But now they are more prominent and more separate from each other. And lambda prime value has much shifted towards the right from the lambda naught value. That means the scattered wavelength value and the incident wavelength value, this difference has become large, and that's why the difference becomes significant. And if we further increase the scattering angle value, that is when it becomes 135 degree, we are seeing that it actually makes the two peaks even more discrete. Like it is now even more prominent to see that the scattered light has a whole different wavelength, has a different wavelength lambda prime than the incident one lambda naught. That means the difference between lambda naught and lambda prime increases as long as we are increasing the scattering angle. So now, what is the like subject? What is the thing that the experiment tries to explain? So basically, the problem is that if again we say that the classical theory were to be true for this case, then the radiation that comes as a wave classically inside the graphite target. Graphite target has electrons sitting inside it, which are like free electrons, and these are stationary electrons. Like they have no velocity, they are just they are just sitting stationary at a place. Their velocity is zero. So we assume that for simplicity, and anyway they are considered as free electron because we are mainly using X-ray. X-ray has a very large frequency, that means its energy is very high. So such higher energy will be enough for any electron to actually come out or actually overcome its binding energy. So with respect to such huge energy, this electron is considered as a free electron almost. Whether in real case never there can be a free electron, totally free electron is not possible, but it is nearly approximate that it is like a free electron and it is sitting in space with velocity equal to 0. And when the wave is coming with the electromagnetic wave classically, it has some oscillating electric field amplitude E. So it has problem with the pen again. So it has some oscillating electric field amplitude E, and so oscillating electric field amplitude E is there, and with this and it has some particular frequency nu. Now this oscillating wave will actually hit the electron inside, the electron whatever is sitting inside, and it actually cause the electron to actually oscillate also in the same frequency nu, because the wave was actually already oscillating with a new frequency. So when it hits the graphite, it also causes the electron inside to oscillate at the same frequency, and because of that that electrons electrons, not electrons, but the light radiation that is scattered off from the graphite will also have the same frequency as the incident frequency, or the same wavelength as the incident wavelength, that lambda prime equal to lambda naught, because it was considered as a wave, because at the wave comes, it has a oscillating electric field value E, which actually makes the electron also inside to oscillate and to radiate energy. The electron oscillate and therefore it radiates energy like the radiator atoms, and the energy radiates will have the same oscillation frequency or same oscillation wavelength like the incident one, like the incident one. So this was the classical theory, all right. So that means if we had to follow the classical theory, then if we just observe the emitted radiation or scattered radiation, the intensity versus lambda, then we'll have a single peak with lambda equal to lambda naught. The lambda naught is the incident wavelength value, and therefore it suggests that the scattered wavelength and the incident wavelength are the same. Lambda prime equal to lambda naught, delta lambda equal to 0. So there is no shift in the wavelengths. Delta lambda is 0, and hence there is no shift, there is no like Compton shift, because this delta lambda we term is at Compton shift. But because experimentally we are seeing that this is not the case in each value of scattering angle, like for each particular value of theta, we are observing that there is a separation between the lambda prime and lambda naught value, and this is a positive difference, like lambda prime is becoming greater than lambda naught. That means inversely nu prime, the frequency of the scattered radiation, becoming smaller than the frequency of the incident radiation. Okay, so this is causing the Compton shift delta lambda not equal to 0. Now this was the problem, and how we'll now see how this was resolved using the quantum theory, how actually quantum theory supported and derived this whole thing. So for that we have to go through a little bit of derivation. So I'll just do it very quickly and I hope you understand it properly also. Just take a space below. Okay, go down. Here, let's say we have to prove how the uh, I mean this thing this from this how we can prove that delta lambda, the Compton shift, is equal to h by MEC into 1 minus cos theta. How we have to prove that? Now just follow this diagram. Here the photon is incoming. Incoming photon has a wavelength lambda and it has an energy E naught and momentum P naught, and it is hitting an electron sitting inside the graphite over here, that is denoted by this xy coordinate origin, like the electron is sitting at the origin. This is before collision and this is after collision picture. So before collision the electron is stationary and free electron at its position, and the photon is coming with an energy E naught and P naught and wavelength lambda. So because in this case the electron is a free electron, so it will only have energy to be its rest mass energy. So basically this is also a physics concept that any particle that is in rest will have a mass that will be equal to its rest mass, and in that case in a body at rest will have an energy that is only equal to is the rest mass energy, which has an expression, standard expression of m naught c square, where m naught is its rest mass. Okay, and if the body has a certain velocity that is not equal to 0, that is it is not in rest, in that case what will be the total energy? So in that case the total energy would be rest mass energy, that is the energy it would have if it would have no velocity, plus the kinetic energy. Of course, because of the velocity there is this excess kinetic energy part that will be adding into the total energy. So that will be addition of rest mass energy plus kinetic energy, and the generic expression, that is the standard one for this case, will be p square c square plus m naught square to the power 4 whole cube, where p is the momentum, c is the velocity of light, and m naught is the rest mass of the same object. This is the total energy in that case. And so the kinetic energy will just be E total minus m naught c square, because we already saw that kinetic energy equal to total energy minus rest mass energy. So this, if this is E total, then kinetic energy of this case will be E total minus m naught. Now this is some brief preview that some of you might have needed if you are not from physics background. Otherwise, these are some standard forms that we all know. So anyway, this is the photon that is incident and this is the electron sitting in its position. And after the collision, this is after the collision, that electron is heated by the photon. Here notice that we are considering the quantum theory, that's where we are considering not a wave-like nature of radiation, but rather we are considering the photon-like or particle-like nature of radiation when it is interacting with the electron. So basically we are dealing with the quantum idea. So that's why we are introducing photon. Now with this idea we will try to derive the value of delta lambda and we will try to justify our experimental results. And so after the collision, so basically it will be like a collision of billiard balls. Billiard balls, you have seen that billiard tables, the balls when how they collide with each other. So in this case also the photon and the incident and the already existing electrons inside the graphite will be colliding with each other like billiard balls, and because of that it will be scattered. The photon will be scattered at an angle theta, which is in this direction, and the recoil velocity that electron will be having from the collision will cause it to scatter in another direction, which is phi scattering angle of the electron in this direction. Now the difference that will be created is that after the collision the wavelength of the scattered photon is changed into lambda prime, and its energy is also changed into p1 and momentum changed to p1 and e1, where initially it was e naught and p naught. And the electron which was as initially at rest, that is it has only free energy m naught c square, but now the electron has some kinetic energy because it has gained some energy or absorbed some energy during the scattering from the photon itself, and which causes the electron also having some non-zero velocity, giving it a momentum p, where p equal to just its mass times velocity mv, and kinetic energy of the electron, where kinetic energy is just total energy of the electron minus its rest mass energy. Okay, so this is the case that we have to know Now we just move on to the derivation below. In this case, so we have drawn a coordinate for our advantage only because it will be easier for the calculation. This is the electron before, and this is the photon coming with E naught and P naught. This is the electron as rates v equal to 0. So only energy electron have is the rest mass energy m naught c square. Notice that we denote the m naught rest mass energy for electron specifically to be me. So we will be replacing m naught with me. It is just the rest mass energy or rest mass of the electron. And after collision, what will happen is that the photon will be scattered off in theta direction, theta angle, and the electron will be scattered off in phi angle. And the electron will have now momentum p, that is non-zero, and it will have a kinetic energy E. And let's assume that it has some total energy or to be indicated by E in this case. Okay? It is the total energy of the electron. Total energy of electron. And similarly, the photon that is again scattered off from here has a wavelength lambda prime. This has wavelength lambda. And now its new energy, because it has given off some energy to the electron, so it will have now energy reduced of E1, and the momentum will also change to P1. Okay. Now let us get the derivation. Now the two major things that will be working in this case, one is the conservation of momentum, linear momentum conservation, that we know is a very basic principle of uh, any physics, like be it quantum, classical, whatever. This is the basic idea that conservation of linear momentum must be true. So this is the one case we'll be using. So let us first discuss this case, that for conservation of momentum, what it have to do is that initially the momentum of photon is p naught along this x direction. So this will consider along x cap direction, and the momentum of photon electron was 0 because it was at rest. So this is 0. This is before collision, and after collision along x direction, what is the total momentum? You see from this diagram that the photon has now momentum p1. So in x component, the component of p1 will be p1 cos theta, and the momentum of electron after the collision is p, and along the x is it has component p cos phi. So basically, to satisfy the conservation of linear momentum along x-axis, before collision and after collision, the momentum should be equalized. That p naught equal to p1 cos theta plus p cos phi. Okay, this is I think you are comfortable. All of you are comfortable with this equation. Now along y cap we do the same thing, that we just equalize the components. So before collision, since the entire momentum was along x, so along y direction there was no momentum at all, so 0 plus 0. And after collision, the y direction component will be just p1 sine theta for photon case, and for this electron's case it will be, since it is in the negative y direction, so it will be minus p sine phi. Now for simplicity, we just simplify this a bit. From here we take it as p naught minus p1 cos theta equal to p cos phi, and from here we will see that p1 sin theta, we take it to the other side, equal to p sin phi. Now these are the two equations. Now we'll just use mm, so we'll just use the simplification that p square will just take a square from both the sides, like this square plus this square. Like this is equation 1 and this is equation 2. Then we'll just do 2 square plus 1 square. This will give us p1 p square sine square phi plus p square cos square phi equal to this left hand side p1 square sine square theta from here, and from here the left side p naught minus p1 cos theta whole square. So if we simplify this a bit, this will be like sine square phi plus cos square phi into p square equal to p1 square sine square theta plus p naught square minus 2 p naught p1 cos theta plus p1 square cos square theta. Now again from here, if we take a common of p1 square, then we will leave up with sine square theta plus cos square theta plus rest of the term. Now we know that sine square x plus cos square x equal to always 1. This is a known result. So we will directly use that and we will obtain p square equal to p1 square plus rest of the terms, that means p naught square minus 2 p naught p1 cos. Okay. So this is very important. This is we denote as equation number 3. Now secondly, just continuing this derivation, we will use the conservation of energy, which is also very crucial in physics problems. Conservation of energy before and after collision should be maintained. So what is the conservation of energy? Now we see before the collision, the now in this case it is important to mention that any photon, it is a standard fact that photon has rest mass 0. Photon's rest mass is always 0. So thereby its total energy E total, that is equal to root over p square c square plus a naught square c to the power of 4 as we described earlier. This second term will be 0 because m not equal to 0, and so the total energy will be Pc. So the photon always have only the kinetic energy part because its rest mass is 0. Now why it is 0, we will not go into the details of that because we don't need that at all. This is just an information that we have to remind that photon has rest mass 0 and this has the total energy as p times c, where p is the linear momentum of the photon. Now so initially the photon has energy E naught and the electron has only this rest mass energy because it was at rest me c square. But after the collision, the photon's energy has been changed to E1. Okay. So in this case, E naught equal to will be P naught times C, because from the above expression you are seeing that for the photon the total energy equal to momentum times light velocity. So in this case, since the momentum is P naught, it will be equal to P naught C. And in this case, since the energy is E1, so it will be again like P1 times C, because here the momentum is P1 for the photon. But for the electron, it has now gained some kinetic energy also, which is denoted by K. Now, apart from the rest mass energy, that is me c square, it has now some additional term, that is the kinetic energy, which gives us this total energy, that is E, denoted over here. Now let us use all of these expressions for the conservation of energy derivation over here, that before collision the energy was only coming from the photon, that is E naught, and after collision, sorry, and there is also this rest mass energy terms from the electron before collision, that is me c square. And after collision, the photon's energy becomes E1 and the electron's energy becomes E, that is the total energy. Again, if we derive this, E is basically the kinetic energy of the electron and plus the rest mass energy of the electron. Therefore, if we cancel me c square from both the sides, we will have E naught minus E1 equal to K. Okay. Or in other words, since E naught equal to P naught C and E1 equal to P1 C, so we take C as common. So C into P naught minus P1 equal to K. This is an expression that we denote by equation number 4, that will be useful for later. And then moving forward, we know that the total energy of the electron is equal to that root over p square c square plus m naught square to the power of 4. So if we just take a square of that, we will obtain p square c square plus m square to the power 4 equal to E square. That is the total energy of electron. So in this case, we just have to substitute some of the terms, like we have obtained from here that and that E equal to K plus me c square for an electron, because electron's total energy is kinetic energy plus rest mass energy. So on the left hand term, we will just replace that K plus me c square whole square, that is E square over here, is equal to p square c square plus me square to the power of 4. Now if we simplify the left hand side, that becomes k square plus 2 me c square into k plus me square to the power of 4 equal to p square c square plus me square to the power of 4. Now these two cancels out. So what happens is that we are left with, now we just, for simplification of terms, we divide each term by c square. So this becomes k square by c square plus this squares cancel out. So 2 me times k equal to this p square. Okay. So this is another expression that will be needed, that will be needing. We term this at equation number 5. Now remember that this is equal to p square and the above term, this equation number 3 also equal to some p square. Now we'll just equate these two equations from 3 and 5, this equation and this 5 number equation from 3 and 5 if we equate, because both of them have p square on the right hand side, we'll just have k square by c square plus 2me into k equal to p naught square plus p1 square minus 2 p naught p1 into cos theta. Now another chance of substitution has come here, because from equation number 4 we have written that k equal to c into p1 p naught minus p1. That means k by c will be p naught minus p1. So we'll substitute that in here, the k expression, that k by c equal to p naught minus p1. So k by c whole square equal to p naught minus p1 and whole square, and k will simply be equal to c into p naught minus p1 equal to this part, the same right hand side. Now we again simplify it, that p naught square plus p1 square minus 2 p naught p1 plus 2 me into c into p naught minus p1 equal to again p naught square plus p1 square minus 2 p naught p1 cos theta. So these terms will be just cancelled out from both sides, and we'll have 2 me c p naught minus p1 equal to p naught p1 into 1 minus cos theta. Okay. Now we have almost come to the end of the derivation. The two, I think I have missed two term, 2 cancels out from both the sides, and it just leaves us with uh, p naught minus p1 by p naught p1 equal to 1 by mec into 1 minus cos theta. Now here we know that we can write this p equal to h by lambda, because this momentum and wavelength has this relation using the uh, this Planck's constant, that p equal to h by lambda. So we can write p naught equal to h by lambda naught. So before that we just have to simplify some of the terms, like p naught by p naught, we only write it as p1, like 1 by p1, and this we write as 1 by p naught equal to 1 by mec to 1 minus cos theta. Now we substitute this part. This is the momentum and wavelength relation of the electron or any particle, is like this is lambda 1 by h, because it's the reverse of that, and this is lambda naught by h, and this is just 1 by mec 1 minus cos theta. Now we come to the final form, that lambda 1 minus lambda naught, h comes on the top in right hand side, h by mec 1 minus cos theta. So this lambda 1 minus lambda naught is basically lambda prime minus lambda, because lambda 1 is what? Lambda 1 is the scattered wavelength of the radiation, which is in the diagram we have denoted as lambda prime, and lambda naught is just the incident radiation, which is denoted by lambda in most cases. So this is the shift in the wavelength delta lambda, the extra wavelength, is equal to lambda c into 1 minus cos theta. This is the Compton shift delta lambda in wavelength, which comes exactly from the derivation of quantum theory, that actually satisfies that our experimental results matches with quantum idea of photon quantum photon idea of taking h nu energy for the derivation. And theta is just the scattering angle, as we have seen, and this lambda c is termed as Compton wavelength, which is given expression as h by mec, where me is the rest mass of the electron, which has also a particular value, and c is the velocity of light, h is the Planck's constant. So now see, if we put theta value equal to 0 degree, then cos theta equal to 1. In that case this will be 0, so delta lambda equal to 0. So we'll just have a single peak of if this is the intensity and if this is the lambda, then have a single peak at lambda naught or lambda, that is the scattered wavelength equal to the incident wavelength, like the classical case almost. But if theta equal to 90 degree say, then cos theta will be cos pi equal to 0, cos pi by 2 equal to 0, so it will be 0, and delta lambda will be lambda c, that is not equal to 0. So there will be shift in two peaks we will see, and the two peaks lambda and lambda prime will have a gap of lambda c, the Compton shift. And similarly, the maximum value, when we will have the maximum value of shift, this will happen when theta equal to 180 degree. That is the incident radiation and the scattered radiation are completely parallel and opposite to each other. That's when theta becomes 180 degree, completely reverse. And in that case, cos theta, cos 180 degree equal to -1. So delta lambda just becomes 2 into lambda times c. This is the maximum Compton shift that one can achieve in this experiment, where this is the same maximum Compton shift, where the peaks are shifted to the maximum value, lambda minus lambda prime, and their gap is equal to 2 lambda. So that's how we are observing these different, I mean, uh, curves that we have obtained from the experiment earlier. Uh, that this was the curve that for theta equal to 0 there is only one peak. Then actually when the theta is increasing in value, then we see the peaks are getting more prominent and they are getting more separated from each other. That means the delta lambda value is actually increasing. So the quantum theory of photon and etc. that actually supported the experimental results of Compton. And this is a simple curve of delta lambda, how it is changing with theta, that at 0 it is 0, and this is pi, this is maximum 2 times lambda c, and at lambda theta equal to pi by 2, it is just a half of that, that is the h by mc difference. Okay. So that's how Compton scattering actually also confirms again the particle nature of radiation. Now let's just to conclude this lecture, we'll just briefly mention that again a phenomenal discovery came after that. After 1923, the Compton effect was also confirmed. Then in 1924, de Broglie, this famous physicist, he in his PhD thesis he proposed a hypothesis which is called as de Broglie hypothesis, which was initially like a hypothesis because he assumed that if light wave or radiation can have a particle nature associated with it, then also similarly all the particles in matter like electrons, photon, etc., these particles can also have a wave associated with their motion that basically governs their motion, and this wave will be called as matter wave. So basically, this was a hypothesis initially because he was inspired by Planck, Einstein, etc. idea of quantum, and he said why not it is possible. So he basically like proposed this hypothesis in his PhD thesis, which was appreciated at that time as a new idea, but it was not convincing for the scientists at that time that such a matter wave is also possible. It's like in the quantum idea, nothing is exactly wave or nothing is exactly particle. Everything is has a dual nature. Everything has a wave nature and a particle nature associated with it. So this was a hypothesis of de Broglie, which was later experimentally confirmed by other experiments, even after a few years. And that's when de Broglie received the Nobel for this hypothesis 5 years later, that is in 1929. So basically, in one line, we can say that the each object by this hypothesis, we can say that each object, be it radiation or uh, any matter, radiation or any matter, can have a dual nature, wave particle duality. That is called a wave particle duality because it have a dual nature. It have a wave nature. Wave nature means it will have a associated wavelength lambda, and it will have associated frequency with it, and it will have a particle nature which will have a energy E and momentum p. And de Broglie suggested that these two natures are connected with each other by this formula that lambda equal to basically uh, lambda equal to h by p, where the wavelength and the momentum are connected to each other by Planck's constant, and mu equal to E by h, where the frequency and the energy actually connected by Planck's constant also. So basically the here is how the wave nature, that is the lambda and mu, is connected to the particle nature, that is the momentum and the energy of the particle. So this is the concept of matter wave that we will discuss in more details in the following classes. But for now, this is a brief idea that we have proposed in here. But I have just mentioned some interesting problems to solve or that we might solve in class, or even you can try on your own, try to solve these problems, and you can come back to me in the next class maybe, because it is already too late. So you can just try and let me know if you are able to solve these problems or not. So these are basically some example problems that I have taken from a book, but for now you just try on your own, and yeah, like using the formula that I have mentioned in the class, and then I'll just help you solve if we are not able to, or if you are stuck at any point. So I'll send you the problems separately, Now, if any of you have any question, I know it's quite late. I did not follow the time. Extremely sorry for that. But still, if you have any question, that then you can ask, or if not, then we can leave the class for. Okay, so no questions from your side. I just hope I am able to explain the physics to you at least to some extent. Otherwise, like, even I am new to this like teaching thing and all. So basically, I'll try so that yeah. So
No,
you have
it's
a
good.
question?
It's good. We understand. We understand.
Okay, okay.
Thank you. Thank you.
Okay, and I'll share my as I am not completed my notes completely. So I'll once I am completed with it, I'll share you again, and I'll be basically uploading it the course any material related to the course in the like in the portal itself. So you'll have to check from there, and I'll share the problems that was not solved in today's class also for you to attend, because it will be nice to like solve problems and get the flavor of the thing we are learning, that actually how we are can solve or apply to problems also. Basically that will be interesting, and at any point if you have any question or a problem in solving the sums, then you can just let me know, or you can just email me, and I can share you the solutions, or I can discuss it in the next class. Okay, so should we then end the class for today? There are not many people left, I see. Okay, then so let us meet in the next class, that is on next Friday. Okay, and see if if some of you are having problem with the time 3:30, then please let me know. Then we can shift it to maybe 4, because otherwise I just wait from 3:30 and nobody joins the lecture. So then it will be convenient for all of us basically. So then let me stop sharing and let me stop the meeting.